All right, so speaking of powerful tools, so we are on to partial differential equations. And so this week we're going to talk about linear partial differential equations sort of abstractly. We're going to go through a couple of examples. We'll talk about the heat equation and the wave equation, or Majid and you will talk about the heat equation and the wave equation on Wednesday and Friday. And those are physical-ish in that they are the same as the continuum mechanics equations that we're going to talk about next week, but under kind of restricted circumstances. So if I heat this table on one corner and don't do anything else fancy, then the heat equation does a good job of spreading the way, talking about how the temperature changes throughout the table. But I can do other things to this table, like break it in half or crush it, or, the heat equation doesn't tell you anything about any of that stuff, but the equations of solid mechanics that we're going to see the following week actually do have all those pieces in it. So the heat equation and the wave equation are kind of specialized, linearized examples of the broader field of continuum mechanics, which includes solid mechanics and fluid mechanics. But next week we're going to see the solid mechanics and fluid mechanics equations in all their glory, with all the bells and whistles and nonlinear terms in them. And then we'll probably end up doing kind of similar homeworks next week that will be, show that you can find the heat equation from the solid mechanics equations under the following circumstances. So we'll try and make those links back and forth. So you can see how the solutions we talk about this week lead to some of the situations we'll see next week in the continuum mechanics case. Does that make sense to everybody? So how many of you are interested in, so I guess, this is one of the questions, one of the things that always occurs to me, which it took me until I was teaching this class to really get a precise answer. What's the difference between a solid, a liquid, and a gas?
We usually say the gas is the only one that's compressible, and then the difference between the fluid and the solid is that the fluid doesn't withstand shear.
Exactly. So we will see how in the equations, how compressibility is represented. And actually solids and liquids are a little bit compressible. So they actually have a compressibility equation, and it describes exactly how much they resist compression. And then the key piece is what the damping agent is. So viscosity in a fluid or in a gas resists shear, but it resists the rate of straining rather than the straining itself. So it's kind of nice to think of like silly putty, which is an in-between case. So silly putty, if you pull it fast, it bounces back. But if you pull it slow, it just keeps stretching. So it's resisting your pulling it apart, but it's resisting the rate at which you pull it apart more than that. So that's kind of the difference between a liquid, which does resist motion, but it doesn't snap back to where it was when you started. So we'll see how the equations will show us that next week, which is cool. All right, but PDEs now. So why do we need a partial differential equation? Didn't we have all kinds of cool things we could do with ordinary differential equations and dynamical systems last week? What's the difference between a partial differential equation and an ordinary differential equation?
Partial derivatives.
Partial derivatives. And so more than one independent direction. So time together with space in derivatives. So what does that allow us to do that we couldn't do with ordinary differential equations?
Have functions in more than one variable.
You have functions in more than one variable, and in particular we can talk about the rate in terms of the spatial rate of change versus the temporal rate of change and the exchanges between those. So in an ODE we could choose either spatial rate of change, like d by dx of something, or we could have temporal rate of change, but we couldn't have both. And we'll see as we get to the equations we're starting to talk about today, and then also especially the heat equation and the wave equation, that what they really are is they're a balance between the spatial rates of change and the temporal rate of change. So the frequency of a wave, its rate of change in time, is closely related to its wavelength, its spatial extent. And so there's an intimate relationship between those things, which is what the wave equation tells us about. And similarly, the heat equation. Things, when you heat in one spot, it spreads out, and depending how spread out it is, it spreads out at a different rate. So the size of the heat anomaly is related to its rate of spread. So those things are linked together. So that's the kind of thing that a PDE allows us to describe that an ODE doesn't. Okay, one of the weirdest things about PDEs is that we almost never solve a PDE in a computer as a PDE. We solve it as a set of ODEs because we discretize it into little boxes. And the little boxes are all little ODEs that are hooked together. So just like we have seen many times, we've thought about, like in our Taylor series approximation, or when we had, the d by dt of something is the limit of, t of the thing, t plus dt minus the thing at t over dt. So if we were to discretize this in a computer, we might actually choose this form with some finite dt. So when we think of how we solve a partial differential equation in a computer, we might think of grid cells that are broken up into smaller grid cells and so on. So rather than taking the derivative, we might just take the difference of adjacent grid cells. So interestingly, when we go to do that, what it means is that we don't end up with partial differential equations in the computer. We end up with a large set of coupled ordinary differential equations. So in your brain, while we're going to talk about the beautiful stuff of taking derivatives and sines and cosines and all exponentials and all the things that are easy to differentiate today, keep in mind that when we get to the continuum mechanics case with the nonlinear systems that we won't be able to write down as cleanly, that we frequently chunk them up into little boxes, and then we're back to solving ODEs. So all that stuff about nonlinear coupled ODEs that we talked about last week is totally directly relevant to solving PDEs on a computer. It's kind of the same thing, just very large sets of many, many degrees of freedom. Does that make sense to everybody? Okay, so let's talk about some PDEs. So one of the simplest ones of all is Laplace's equation. And let's just do it in 2 dimensions. Okay, so what is this funny upside down triangle? I told you guys the story about the upside down triangle in my oceanography class, right? I've been lecturing for like 3 weeks, and somebody finally raised their hand and said, I'm sorry, what's the upside down triangle? So as you can see, here we are, 9 weeks into this, or 10 weeks into class. The upside down triangle is hard to think about. So what does this operator mean?
It's like the double gradient.
It's like the divergence of the gradient. So it's d dx squared, curly d's, because it's a partial derivative, plus d dy squared equals 0. Okay, we had just one of these. Can you solve that equation? Yeah, because that's an ODE, second order, linear, homogeneous ODE. It's actually even simpler than that because there's just one of them, so you don't even have a thing on the other side. We have the tools to think about how to solve that. We actually have almost the full. We can integrate both sides. We get a constant on this side, we get another one, and we integrate again, and we get a linear function. What about this? That's different, right? Is it homogeneous? It is, because we don't have anything that's not proportional to phi. So if we set phi to 0, the whole thing will go to 0. So what in our ODE case made our homogeneous solutions not equal to 0? We talked a lot about collapsing into a steady state or blowing up away from a steady state. But we didn't talk so much about just starting at the steady state, which is where every term in the equation is 0. So what do we have to do then to make the terms in the equation be not 0? What additional piece of information do we get beyond this thing? It was kind of implicit when we drew our phase space things. You know, we have a whatever, we have an intersection, we have another intersection, so there are steady states, and I'd say something else, which was, what if we start out over here? So what is that thing when I say, what if we start out over here? What do we call that?
Perturbation.
A perturbation or an initial condition. And our initial condition was not necessarily at the steady state. So our initial condition was the thing that actually gave us an interesting, variable minus the variable at the steady state version. That was not equal to 0 because we said initially this was not equal to that. So we got some interest in our equation. So even though there are homogeneous equations of v minus v star, we didn't start off with v equal to v star. So we didn't make the homogeneous equation 0. So there's something equivalent here, but we don't call it an initial condition, we call it a boundary condition. Because in this case, there's no time in this equation. This is going to be, these could be functions of time, but this equation doesn't describe their behavior in time, it just describes their behavior at a given instant. We didn't have any derivatives with respect to time. So rather than an initial condition, we talk about a boundary condition. And so the boundary condition needs to be additionally specified in addition to this equation. This equation is called the field equation because phi is the field. So what's a field again? We talked about scalar fields and vector fields, but what is a field? Jean, go ahead.
It's just like a set of things, be they vectors or scalars, defined for a whole plane space.
Yeah, it's defined in a lot across space. So we talked about it a lot when we were talking about partial derivatives. It's something you can take the partial derivative because it's got a value everywhere. So in continuum mechanics, it is the thing that is continuous that makes it a continuum mechanics. So it's like there's liquid everywhere. So that liquid has properties like density and temperature and velocity. So it could be a scalar, it could be a vector, but it's a field. So this equation, the one that applies throughout the field, is called the field equation. And then the boundary condition is the thing that applies only at the boundaries of the field. So if we're talking about the temperature in this room and we wanted to use Laplace's equation, the field equation would apply everywhere in here, but the boundary conditions would apply at the wall where the air ends and something else happens. So we might wonder what kind of boundary condition we want. It might just be that the air doesn't get to go through the wall, and permeability is a good boundary condition. It might be that the air can't lose heat to the wall, so insulating boundary condition. Those are the things that come in as boundary conditions. Does that make sense to everybody? Okay. So, more about this equation. Okay, so there is a standard solution method which works. I hate to say it, but I think it works for every equation we're going to talk about as PDEs, which is a little bit of a cheat because it doesn't work for the continuum mechanics equations next week. But it's a way to begin. Okay? So what if we assume that phi, which is a function of both x and y, is actually composed of a function of x times a function of y? And we could get super fancy and remember, so is this a linear differential equation? It is, because all it has is derivatives, and derivatives are linear operators. And so if we have one of these that works, we might expect to have more than one of them. Just like we had, when we had a second order ODE, we came up with two different general solutions, and we just added them together. We might expect to have more than one general solution here. So let's put a sum down, give each of them an index, and sum over all the values of that index. Okay, so this is a nice guess form. So what does this mean? How restrictive is this for one of these to be this expression? What does it mean that it's independently dependent on x and y and their product? Think about it in this room again. Suppose it's constant in this direction, whatever the field is we're talking about, but it varies in this direction. Is that allowed in this form? We say that's y and this is x. It would be, because constant in y is just a function of y, which is a constant, and then it would just be a function of x. So that's not too hard. Or vice versa the other way. Or I could say it was sinusoidal in y, but that the peak of that sinusoid was always at the same location as I went this way, even if it goes up and down. Sorry, can't figure it out. So suppose we have a wave-like thing that's going like this. If I go to one of those waves, it could go up and down, but all the other waves would go up and down in phase with it as we go this way. Does that make sense to everybody? So it's the things that are disallowed are things that are like connections between the x variation and the y variation. So over here, there's something special that's happening that's not happening in any other place in the room, which is isolated in both x and y dependence together. This says the x variations are independent of the y variations, and the y variations are independent of the x variations. You can get variation for both of them, but that's not everything. So it's not every possible function you can think of, but it's a lot of them. Okay? And you're going to see in a moment why this is a really convenient thing to do. Okay, what happens if we plug this into here? What's the second partial derivative with respect to x of this monster? Does the second derivative with respect to x affect the y's? Doesn't care that I'm summing either. It just pops right through. So what I get then is I get x double prime of x, y, and y. And I can do the same thing. Okay. So then what does my total equation look like? It looks like the sum over k of x double prime y plus x y double prime equals 0. Right, I'm just putting this one, adding this to this, bringing the sum up. Yeah.
Why have we chosen to relate the big X and big Y by multiplication?
Because we have.
Oh, okay.
That's an excellent question. We are also allowing there to be a sum, but we're relating them by multiplication. And we did it because of the way that derivatives work in linear functions, because I'm about to show you something in 2 lines that's going to make it clear why multiplication is a really good choice. Okay, the first thing we can say is that if we remember back to our linear, adding together different linear solutions, it would be really convenient if not only the sum of all these satisfied this, but actually each one of them individually. So if I drop the sum and just make every single k satisfy this equation, it's clear that that makes the sum also satisfy the equation, but it's actually an additional constraint. And it turns out this is a separate step you have to prove after you find the solutions, to say that the solutions actually include everything and that they could be treated separately. But let's just assume it's true, and then we'll come back to it when you see the solution at the end, and we'll actually already have that result in the bag from previous stuff we talked about. Okay? So, x double prime of k, y, k, plus x, k, y, double prime of k, equals 0. And I'm not. So this is a homogeneous system still. So I don't want y or x to be equal to 0. So I can divide by y or x. And I'm going to divide through by y, x times y, the whole thing. X times y on this side too. This side is just 0, but this side now becomes x double prime k over x plus y double prime k over y. Okay, and the right end of these depend on, just to make it totally explicit. Okay. Or, even to make our lives even simpler, let's put these on opposite sides of the equation. So this is why we wanted them to multiply. This side of the equation depends only on x. So only depends on this direction in the classroom. This side of the equation depends only on y. What does that mean about these two functions? Can they vary with x? It can't vary with x, because if it did, then something that varies with y would have to equal something that varies with x. Vice versa, this side can't vary with y, because if it did, then you'd have something that only depends on x would have to equal something that only depends on y. So they both have to be constants. And we'll make it squared for a second. This can't depend on x, but all it depends on is x. This can't depend on y, but all it depends on is y. Therefore, they're both constants. And they're equal to the same constant. This is called the separation constant. Because I have just separated the two variables, the x's and the y's. This method is called the method of separation of variables. But now look at what we just written. I can forget about this and write this equal to c squared 2. What kind of a differential equation is that? If you want to rewrite it this way, c squared x of x equals x d by dx squared x of x. What kind of a differential equation is this? Second order. What's this part? Constant coefficient. Ordinary differential equation. We just started with a partial differential equation and made two ordinary differential equations out of it. We already know the answer to this one. What's the answer to this one? X equals e to the c x. I guess there's a plus or minus. So we have two different, let's do it all the way out. Plus x minus e to the minus cx. Everybody see? What about the y equation? It's a little bit different because there's a minus sign here. Squared away with writing my y's. Y. So that's, what kind of equation is that? Second order, linear, homogeneous, constant coefficient. So we can write the solution to that. And there's only one difference. Why does it write an I? Take the second derivative of this, I need it to be minus c squared times itself. So I wanted an I in there. So how did I decide to put the I on the y equation and not the x equation? Was there any like rationale? I just picked it. I just said, hey, c squared. I could have said minus c squared and it would have flipped it. And all I knew was that it was a constant. I was just sticking in something that would be convenient to make the algebra work out right, but I could find, when I go to the next step with these two solutions, that c actually has to be an imaginary, in which case these become the real ones, the real exponents, and these become the imaginary ones. What I can't do, though, is I can't have real in both. Okay? So when we look at these sum over these possible linked solutions, one of them is going to be exponentially decaying or exponentially growing, and one of them is going to be oscillatory. That's what this equation tells you. The Laplace equation says you can oscillate in one direction, but you have to either exponentially grow or exponentially decay in the other direction to make up for it. Now we can have oscillating in this direction and exponentially decaying in that direction and add them together in this magic sum. But within each of these matched modes in the separation of variables, it's going to oscillate in one direction and decay in the other, or oscillate and grow in the other. So how do we, what's the next step after now we've written down our two general solutions. What's the next step? How do we find what these C's are and what these pluses and what these coefficients are? What do we need to bring in to bear? Now we have the boundary condition. So the boundary condition would tell us where the walls are that would help us define these y pluses and y minuses, and frequently it also puts a constraint on what the c's can be. Okay? Does that make sense? So that's the way, that's the Helmholtz equation, that's the Laplace's equation. Okay? What if you make this slightly more complicated? Just slightly. So I go through an example with boundary conditions in the notes, which is just kind of a lot of algebra, which gives us a specific solution. And I show that it doesn't matter which way you pick the order of the separation constant, whether you made it negative and then go to the end or vice versa. Once you go through all those steps and match the boundary conditions, you end up with a solution. You can make weird choices along the way, and then they all fall back apart when you match it to the boundary conditions and you get back to the same thing. The general solution form isn't unique, but the full solution, including the boundary conditions, will be unique. Okay? So let's look at a Helmholtz equation, which is helpful because it will be, when we do separation of variables on the wave equation and the heat equation, the Helmholtz equation is going to be a temporary part of that. The Helmholtz equation looks just like this, except it has this. So this is just some constant that's been given to me. That's part of the framing of the problem. And it turns out it'll be the separation constant when we do separation of variables for the wave equation and the heat equation. So this is anticipating the steps that Najid is going to take you through on Wednesday and Friday. Okay. Can I still do this? Yeah, I mean, I just guessed it anyway. So I guessed the same thing that I guessed last time. Why not? Is this still true? Yeah.
So is that just a valid form of writing any equation for you? Are you saying you could do that for any equation?
No, we can't do this for any equation. Oh, sorry. Let's rewind. I didn't say this explicitly. What are these things if they're e to the plus I c y's? Sines and cosines. Can you express any function at all with an approximation in sines and cosines if you're willing to sum over a large list of sines and cosines? So I didn't know it to begin with, but what it turns out is that because sines and cosines come out as the answer to this problem, and we know that sines and cosines can approximate any function, that the solution that came out tells us that if we sum over all of them, we can express any function we want. And so the only thing that's constrained is if you have a sine or cosine in this direction, you have to have the matching decay function, the exponential in this direction. And since it was arbitrary whether I had sines and cosines this way or sines and cosines that way, I can get anything I want and starting out from that, and then the other direction just neatly matches to it. So that's a good point. This sum here kind of didn't play much of a role. We said, oh yeah, don't worry about it. We'll be able to do something fancy if each of them individually satisfies it, the sum will be a more general function. That's exactly the point. When we go backwards from here to there, we now gain any function we wanted whatsoever for all of the boundary conditions, because we can always expand them as a Fourier transform, and then we get the other part of the solution from that. That makes sense to everybody? This is why we needed Fourier transforms at the beginning. We needed them at this point. And in fact, the Fourier transform was developed by Fourier in order to solve the heat equation, which is the next thing we're going to talk about on Wednesday. So we use Fourier transforms for lots of things, but this was actually the reason why he came up with it in the first place, was because he wanted to solve equations that looked an awful lot like this, because he wanted something that when you differentiate it, it becomes a simple product times the thing itself. So he built a function composed of all sines and cosines in order to attack these kinds of problems. Does that make sense to everybody? Okay, cool. All right, this is still true. Once I assume this is still true, this is still true for this equation. This equation is a little bit different because now we get right? Everybody on board with that? Does it still make sense to divide by x times y? Yes, because I have x times y here too. So I get k squared equals 0. Okay. Cancel x and y here, cancel x and y there. I have something similar to what I wrote before. But what is it this time? Plus k squared equals 0. So now we have to be a little bit more tricky at this stage. If I move the x function to the other side of the equation, so all the x's are collected on this side, can that depend on x? This ratio. It can't, right? Because this can't depend on x because it doesn't have x as a variable in it. And this also can't depend on x because it's just a constant. Or vice versa, if I move the y part to the other side of the equation, can it depend on y? No, it can't because this doesn't depend on y and neither does this. So we have the same separation assumption, except now we've got to keep track of these k squareds. So instead of c squared times x equals d by dx of x squared, we have to be a little bit more careful. So we can write this as two different differential equations. Think about how to do this. There are a lot of choices here. This is gonna be some constant, and this is gonna be some other constant. So let's just call this one m squared, where this one n squared, where y double prime over y equals n squared. And so in both cases, we end up with a similar kind of equation. We have m squared here, and we have n squared here. And so we have n up here. We have m here. Oops, sorry. N here. We have m here. We have n here. So it looks an awful lot the same, except the one piece is different. Last time, this one oscillated, this one didn't. What's the different logic now because of this equation? Why did we get the oscillation last time? Because one of them had to be negative if the other was positive, because they had to add up to 0. It's not quite the same now, because both of them could be negative and cancel the k. Or one could be positive, the other one could be negative, but not as negative as this one is, or not more negative than this one is positive in order to cancel the k. So it's now a three-way game, so we can have oscillations in both directions in this equation, instead of oscillation means to k. So this little extra term doesn't make the problem inhomogeneous, doesn't make the problem inhomogeneous. It's still a homogeneous equation. We still need to use the boundary conditions to determine all the coefficients. We still have to play all that game the same way. But now we have a little bit more freedom in these separation constants and what they can equal. But otherwise it's the same equation. Which is kind of obvious, because what if k squared happened to be 0? What's that? It's the old equation we just studied. So we better include, in the special case, the k squared equals 0, the solution to the old equation. So we've gotten it back, but now we have more possible solutions as well. Does that make sense to everybody? So maybe we should go through the process of looking at what the boundary conditions look like. It's how irritating. Sorry. Oh, no, we should talk about something even better.
David,
Yeah.
overall, so are we just saying that if we have a function b and it satisfies Laplace's or Helmholtz equation, then we can break it down into ODEs?
It's actually more general than that. For these two functions, a separation by variables approach works. We can even do separation by variables under more complicated circumstances. It's something you can always try and see if it works. And the if it works part is, can you break it up where you put all the dependence on one variable on one side of the equation and everybody else on the other? Like the separation stage is this little bit of algebra here that says I was allowed to collect all my x's on one side and leave all the y's on the other. Or if we had one, we could have done this on x, y, and z, and then I would have just pulled the x's to one side and left all the y's and z's on the other. But the logic of that, can this depend on x? No, it can't, because the other side doesn't. That continues to happen, which then allows you to pull apart and separate those. Does that make sense?
So these are for only functions that satisfy Laplace's equation? Or Helmholtz equation?
So Helmholtz and Laplace are examples where the separation of variables approach works. But you can try this separation of anytime you want and see if it works. And so it might mess up right here, might fail to be able to be separable. So most equations are that way. Or it might fail when you get over here and you see what the solutions look like. They might not be a complete set. That would be rare in homogeneous equations, but in an inhomogeneous equation, you might get a particular solution here that kind of screwed up everything. And then you wouldn't be able to match the boundary conditions. So that's a separate bit that this could fail. But for all of the systems that we're talking about, separation of variables is a decent way to go. There are lots of other much more obscure methods of solving PDEs, but this is a nice one to start, especially for linear PDEs that are the kind that you find here. So remember how, there are a couple of things we could say. What if I had done this in polar coordinates? I could have written the Laplacian in polar coordinates rather than x's and y's, and I could have tried a separation of variables with an r and theta. I could have tried that, and maybe it would have worked, maybe it wouldn't have. There would have been some other terms in here, because the Laplacian has a few other terms in the polar coordinate form. So that's a good example of something you could try. When would that be convenient?
Maybe when a problem is spherically symmetric.
Yeah, so here, we're talking about our room, we've got Cartesian walls that our boundary conditions are going to come on, but if our room was cylindrical, that would have been really convenient, because then all of our boundary conditions would have been imposed at the same r, just varying in theta. If we solve this problem on a sphere, we could do it as well, separation of variables, and the answer that comes out of that are the spherical harmonics. The spherical harmonics pop out naturally then they are convenient when you're talking about things on a sphere that have a Helmholtz or Laplace-like behavior. Does that make sense there, right? Interestingly, so I said that sines and cosines pop out of this. So do the spherical harmonics, so do the Bessel functions, so do the Airy functions. They're all special functions are intimately related to solutions of the Helmholtz and Laplace and equations. There's a general kind of differential equations, and when you do a construction method like this, the things that pop out of that system are really robust, and so you can actually prove that they are always like the Fourier series, that they're complete and orthogonal in the same way and under the right circumstances. So we're scratching the surface of a much bigger field of stuff that's called Sturm-Liouville problems. These are examples of that kind of differential system. But we also could have just done this guess and check, which in the lingo of atmosphere, well, in the lingo of geophysics is called assuming a plane wave solution. So we could have said, what if we just assume this thing is like e to the I mx e to the I n y. We could have plugged it in, bloop, 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 and we would have found exactly the same equation. So we could have done a guess and check by having done this a few times and knowing that we always end up with exponentials, because this is a homogeneous differential equation. That's, when you separate it, it's going to be two homogeneous ODEs, and the homogeneous ODEs always have exponentials as their solution. So this is kind of, our guess and check just looks like the product of our ODE homogeneous systems with a sum over all the m's and n's that you would want. Does that make sense? So we'll have more practice on this week. Then next week, we'll see how these Helmholtz and heat equations and wave equations pop out of the continuum equations. And then I'll start to make some of the linkages there. The rest of the behavior of those equations is why you have to go and take classes like the one that Chris Huber and Victor Sy are teaching next semester on continuum mechanics. Then you'll study solutions and solutions and solutions of these equations, but those equations, not just the simplified ones. Does that make sense? Cool.